Having thought about that issue, let us put this into practice, where for a particular design, we have specified a failure force to exceed to be at least 10 power 5 newtons. The stiffness should be at least 3 into 10 power 7 newton per meter, and the length is specified to be exactly meter. The area is free to be changed. And we have to select from these 3 different kinds of materials, starting from a steel, and if you were to swap it with an aluminum or a titanium, how do we put these considerations? Which material do we choose that meets these constraints? So we know that one mass that we can compute based on the stiffness limited design is L square times S times rho over E. So if you can compute rho over E and substitute for L and S, then you would compute a number of different masses. Give it a try, and it's good to be able to get through the exercise. And basically, if you pay attention to the fact that E is in gigapascals, you will be able to get a number that is about 1.15 for not only steel, but roughly the same for aluminum and titanium. 6 aluminum, 4 vanadium. That's what Ti64 stands for. If instead, now you compute a mass based on a strength limited design, right? So we know that that mass can be computed using L times the failure force F and this rho by sigma 1, okay, which can be different for each material combination. 7850 by 320, 2700 divided by 120, 4400 divided by 950. And so knowing that the yield strength is in megapascals, and if you substitute that, basically you begin to see that based on the strength limited design, as you go from steel to a titanium, you end up having a mass that keeps reducing, right? So the mass that meets the criterion in each of these cases is quite different. So we had gone through the process of choosing a mass that would satisfy both these criterion at a minimum. So that mass would be 2.45 kilograms in this case, the larger of these two. For steel, for aluminum it will be 2.25 because that would be the larger of 2.25, 1.16. For titanium, 6 aluminum, 4 vanadium, it will be the larger of 0.46 and 1.15, so it's 1.15. So basically now, for the material selection, the material that gives the lowest mass while satisfying both the constraints, stiffness limited and strength limited, is 1.15. And so you would end up choosing titanium alloy for this tie rod. So if you made a plot of M1 versus M2, you basically have different combinations. These dots represents combinations of M1 and M2. If the second constraint is dominated, you will have points lying on this area above this line where M1 is equal to M2. And then you have points below that line, which is when constraint 1 is dominated. Basically, you select this lowest point over here that meets both those constraints. And so 1.15 will become the best choice. That's highlighted by this dark circle. Try to plot these points and make that determination. There is another definition over here called the coupling line, okay, represented by this dashed line in red, ending with an arrow. What does that mean? That represents the situation where you set the mass obtained from constraint 1 to be equal to the mass obtained from constraint 2. When is that possible? That is one type of question. The second question is to note that here, in this case, for each value of S, L, and F, these things will change. When you select the two masses to be equal to each other, computed by the two methods, you basically have a scenario where if you rearrange terms, you have a material index M2 will be equal to a material index M1, in this case these two, and you have LS divided by the failure strength. If you plotted now the material index, the two material indices, as opposed to the two masses in a log-log scale, you basically come down to a situation where now this intercept, which is basically the slope of this line that connects M2 to M1, becomes defining and independent for various combinations of L, S, and F. So instead of plotting mass 2 versus mass 1, if you plotted material index 2 versus material index 1, you end up having the ability to look at various combination of L, S, and F, as opposed to creating a new chart for each combination of L, S, and F if you only plotted mass against mass for the two different methods. So this is the power of material indices in one more variation, where we have taken advantage of ability to derive material indices and be able to plot them, especially using CES EduPack. And now we can add slopes of different lines. We can adjust the intercepts up and down on the CES EduPack and begin to look at what happens when this, because this is a log-log scale, right? What happens when we change this intercept, or if it's a non-logarithmic scale, what happens if we begin to change the slope? Let's give it a try in terms of what happens when you plot the material index of rho versus E versus rho versus sigma Y. Give it a try on EduPack and look at whether you can come to this answer for Ti64 alloy. This particular constant over here, Ls by Ff, is called the coupling constant. And now for different values of L, S, and Ff, you can be able to move this up and down, okay, in this log-log plot. So mainly what you have as a powerful representation of material index is that once you have represented different attributes of materials, which are represented by these dots, okay, you will be able to take into account different loading conditions and different geometry conditions that are constrained within the design, and be able to choose different materials for different design variations from a single plot. So our design exercise as we move during the next couple of weeks will be to implement this aspect of learning. So this is in the case of multiple constraints and a single objective.